Мне тогда скомандуйте, когда запись начать.
Да, давайте начинаем запись.
Всего хорошего.
Good afternoon, everybody. Welcome to colloquium. Today our speaker is Cianchi, and he will talk about symmetric gradient Orlicz-Sobolev spaces.
Thanks. Many thanks to the organizers of this celebrated seminar, in particular Sasha Nazarov. And today I'm going to report on some joint work with Dominic Bright from the University of Edinburgh about some recent joint work on certain properties of functions in Sobolev spaces defined in terms of their symmetric gradient. So let me start by recalling some basic notions and mainly fixing some notations. So I'll be concerned with vector valued functions. So everything here is relevant only if functions are vector valued. And this means that I'm dealing with functions u, which are defined on an open set omega in Rn, which take values in the same space Rn. And n will be any integer larger than or equal than 2. Now, since we have vector valued functions, then the weak gradient is a vector valued matrix taking values in Rn times n. And these kind of functions are well known to be fundamental in the analysis of systems of PDEs. And in particular, a function space that enters the study of these systems is the classical Sobolev space, which I denote by W1P naught. And this consists of those functions in LP whose gradient is also in LP. And for the time being, I'll be dealing with functions that are 0 on the boundary of the domain. So that's why I have this not in the notation of the space. It's also known that for some physical phenomena, which are described by this function u, what is entering the problem, the model, is not the full gradient, but just the symmetric part of the gradient, which means the symmetric part of the matrix, which is given by this formula, which I denote by epsilon u, which is 1/2 of nabla u plus the transpose of u, of nabla u. This is the case when one deals with fluid dynamics, and in particular, generalized Newtonian fluids, where nonlinear phenomena come into play, or even in the description of plasticity phenomena or nonlinear elasticity. So for these function spaces, which are defined in terms of the symmetric gradient, there is also a theory, and in particular a theory of the Sobolev spaces of this kind, which I denote by E1 not LP. And in analogy with the classical definition of the Sobolev spaces, these are defined as those functions in LP for which the symmetric gradient also belongs to LP. And in this case, they also vanish on the boundary of omega. And this can be defined for any P between 1 and infinity. Now, it's clear that since we have a weak assumption on just a symmetric part instead of the full gradient, the classical Sobolev space is continuously embedded in this symmetric Sobolev space for any P between 1 and infinity. Now, what about Sobolev type embeddings for these symmetric spaces? Now, if P is strictly between 1 and infinity, then the situation is quite trivial, because for this range of values of P, the full Sobolev space and the symmetric gradient Sobolev space agree. This is due to a famous inequality called Korn's inequality, which tells us that for any such P, then the LP norm of the full gradient is estimated up to a constant by the LP norm of the symmetric gradient, so that the two spaces agree. Let me remind you that on the other hand, this inequality is false if P is one of the two endpoints, which means P equals 1 or P equals infinity. Now, because of this Korn inequality, as I said, the Sobolev embeddings for E1LP are exactly the same as those for W1LP. And in particular, this symmetric gradient space is embedded into LP star, where P star is the standard Sobolev conjugate NP over N minus P, if P is between 1 and N. It's embedded into L infinity, and even in the space of Hilbert continuous functions with exponent 1 minus N over P, if P is larger than the dimension N. And in the borderline case where P equals the dimension, then one has this embedding into the space exponential N prime, where N prime is the conjugate. And this is the famous Udovich-Forsyth-Trudinger embedding. Now, this embedding can also be proved avoiding this Korn inequality, but just making use of representation formulas for these functions with symmetric gradient in terms of integral operators whose singularity is the same as that of various potentials. So in a sense, using the original approach by Sobolev for his embedding. Now, as I mentioned, since Korn inequality fails for P equals 1, then in fact the two spaces, the full classical and the symmetric Sobolev space, are different when P is 1. However, the same embedding that holds for the space W11 is true also for the corresponding symmetric gradient with symmetric gradient in L1, which means that this space is embedded into Ln prime, where n prime now agrees with the Sobolev conjugate of 1, as you know. Now, how to prove this embedding here? A proof of this embedding is similar in the method as the proof for the Sobolev space W11, which was given by Gagliardo and independently by Nirenberg, and that is different from that by Sobolev, which in fact does not apply. Now, it's interesting that neither of the two approaches that I have mentioned for P larger than 1, which means Korn inequality or representation formula, works for P equal 1. And conversely, this approach of Gagliardo and Nirenberg type that works for P equals 1 doesn't apply for P larger than 1. So the two situations are quite different in a sense, and there is a gap in the proofs between the two. It's interesting that there are some mathematical models for some systems for which the nonlinearity which governs the mathematical model is not just of power type. An example of this is that of what are called non-Newtonian fluids, for which here I've written a basic model, where U is the speed of the fluid, pi is the pressure of the fluid, rho is the density, F on the right-hand side represents the volume forces, and this function A, which appears through its derivative, is in general a Young function, which means a convex function which vanishes at the origin. So of course, the function t to the p is one instance of Young functions, but here one can have something more general. And the study of this kind of mathematical models requires Sobolev type spaces that are built upon Orlicz spaces instead of Lebesgue spaces of type LP. This I will denote by E1LA, where A is this Young function, and they are defined in a similar fashion as the symmetric gradient spaces by requiring that U is in the Orlicz space LA, and that also the symmetric gradient belongs to LA. again, so far I'm dealing with functions vanishing on the boundary. Let me recall that the Orlicz space LA is defined as those functions for which this integral here is finite for some lambda larger than 0. Now, an example of a fluid which is governed by this kind of nonlinearity is what are called the prime iron fluids, which go back to several decades ago. And for these fluids, the function A is just slightly faster than linear near infinity. So it behaves like t times a log. Another instance, which arose more recently, is given by certain fluids which are used in body armors. So for these fluids, the behavior of the function A in the model is of exponential type. So in the next slide, if it works, I have a video illustrating the behavior of these fluids. And let me just tell you that the peculiarity of these fluids is that they have to be, flexible enough to be filled in these armors and to fit around the body of a person, but they have to have the property to harden quite immediately if they are hit with a high pressure, typically a bullet which is shot by a gun. So here is a video where you see this is a fluid, and this ball is floating on the fluid because it's going fastly. But and these people are jumping on the fluid, so there's a high pressure on the fluid which responds by making them not sink in the fluid, as you see. But in the end, you will see if they stop, they immediately sink. Here is the situation. So the response to the fluid is different depending on the pressure which is on the fluid itself. And these have an exponential growth in the model. Good, so let's go on with mathematics. And so the question that we addressed is the one of Sobolev embeddings for this Orlicz type symmetric gradient spaces, which would generalize the embeddings I've just reminded to you for LP type symmetric gradient spaces. Now, this question was raised to me several years ago by Miroslav Bulicek and Josef Malek in Prague during a long visit of mine, and they are well-known experts in nonlinear fluid dynamics. And probably the reason why they asked this question to me is that I had considered and solved a similar problem some years before for the standard Orlicz-Sobolev space W1LA, where the full gradient is required to belong to LA. Now, it turns out that none of these methods that I've illustrated briefly to you for the LP case applies if t to the p is replaced by an arbitrary Young function A. And so in particular, the Corny inequality that holds for p strictly between 1 and infinity in general fails for an arbitrary Young function. It does hold, and this is the formulation, if A is satisfying both the so-called delta 2 and the nabla 2 condition. So I'm not going to give these definitions now in detail. Let's just say that delta 2 is a doubling condition for A, and nabla 2 is a kind of reverse of the delta 2. In particular, this simultaneous property prevents A to be too close to a linear function, which corresponds to p equal to 1, and nabla, this is a nabla 2, and the delta 2 prevents A to grow too fastly, which corresponds to, let's say, exponential type growth. And this was proved in this paper by Martin Fuchs and Dominic Bright and Lars Steening. Special cases are also in a paper by Acerbi and Mingione, who dealt with this kind of nonlinear problems for elliptic PDEs. Now, in fact, a version of Corn inequality is available even if these assumptions on A are dropped. But then the inequality in general takes a weaker form, in the sense that the Young function that appears on the left-hand side of inequality, the one that takes into account the full gradient, can be slightly weaker than the right-hand side. Specifically, this is the inequality in question, where you see you have LA for symmetric gradient and LB for the full gradient. And the balance between A and B is given by these two conditions, which involve A and B and the Young conjugate that here I denote by tildes. And this was the sufficiency of this condition was shown in this paper of mine. And together with Dominic Bright and Lars Dinning, we also proved the necessity of this condition. So this gives a full characterization of this Corn type inequality for arbitrary Young function A. Still, the use of this inequality doesn't allow for an optimal Sobolev embedding, because here you see that there is a loss going from A to B, which is inevitable for Corn inequality, but apparently is not reflected in the Sobolev embedding. Now, with Dominic Bright, we attached this problem, and in fact, we considered it in a more general setting, where instead of considering just Orlicz spaces, we took into account what are called rearrangement invariant spaces on omega. And then we consider symmetric gradient spaces E1x, which are defined as those functions which belong to the space X and whose symmetric gradient also belongs to X, and they are zero on the boundary. So what is rearrangement invariant space? I think that in Russian literature, they are also called symmetric spaces, as far as I remember. So I'm not going to give a full definition again, but the main feature is that the norm of two functions in this kind of spaces is the same if their decreasing rearrangements agree, or equivalently, if they have the same distribution function, so the same measure of level sets. So in a sense, these kind of norms only take into account the size of a function, but not finer properties like oscillations or derivatives, these kind of things. So here there is a picture how to build a rearrangement of a function. You start with an n-dimensional function, and you end up with a one-dimensional function, which is depicted in this red graph here. And the link between the two is that this one-dimensional function is decreasing, and the measure of each level set of this function here, the one-dimensional level measure, is the same as the n-dimensional level measure of the original function that was there. So integrability properties are preserved under this operation of rearranging. Now, this comment I already made, and the typical examples of rearrangement invariant spaces are the Lebesgue spaces LP, Orlicz spaces that I've been talking about so far, and also Lorentz spaces. I'll give a definition of Lorentz spaces in special instances that will come into play soon. Now, before giving the general results that we obtained and the precise statement, let me tell you in advance what are some general traits of these embeddings that we got. And the point is that these features of the embeddings for these spaces X are different depending on whether we are in the subcritical regime or supercritical regime. What do I mean by these two expressions? So subcritical means that the best possible target for an embedding on this space E1X is in fact just a rearrangement invariant space. So it's just a space defined in terms of integrability of functions. This corresponds in the classical case to the situation when P is less than or equal to N. By supercritical regime, I mean the situation where one has embedding to L infinity, but even more, one has embeddings into spaces with a modulus of continuity, Hilde continuity in the classical case. Now, and this corresponds to P strictly larger than N. Now, the first situation, when we have embeddings into a rearrangement invariant space, it turns out that the embedding for the symmetric gradient are always equivalent to embeddings for the full gradients of Orlicz spaces, in the sense that if one has embedding for the symmetric space into some space Y, then the same embedding is true for the classical Orlicz space with the same domain X. So there is no gap between the information which is given by the symmetric gradient and the full gradient in this subcritical regime. Situation is different if we are in the supercritical case, namely when we deal with embeddings into spaces of continuous functions, because here it may happen that, so here by C sigma, I denote the space of uniformly continuous functions with the modulus continuity sigma. Sigma is a function now. Now here it may happen that the space with a full gradient in X is embedded in some space of this form, but the space with just the symmetric gradient in X is not embedded into the same space of uniformly continuous functions. So embeddings for symmetric gradient spaces in this range can essentially be weaker, not always, than the corresponding embedding for full gradients. Now let's go to some precise statement, and let me begin by considering this problem of the optimal Orlicz target space for E1LA. So here, I assume for simplicity that omega has finite measure, and starting with this function A, we construct another function, A sub n, another Young function, according to this rule. First, we build up this function H, defined by this integral here, and then A of n is given by the composition of A with the inverse of H. One can verify that this is still a Young function. And before giving the statement, let me tell you and bring your attention that in this formula and in other formulas that we'll see later, one could be scared because of the computation of these integrals and inverses in the formulas. However, in the definition of the Orlicz spaces, for instance, when omega is finite measure, what is relevant is only the behavior of the Young function near infinity. So it's only necessary to know the asymptotics of this function h and h minus 1. And in all practical situations, this can be easily evaluated, as you can imagine. Now, the statement is the following. Given a function a as above and constructed this function a sub n, this embedding holds from E1LA into LAN, and there is a corresponding Sobolev type inequality or Poincaré type inequality for functions in the space which vanish on the boundary. And what is important is that this target space here is optimal, which means the smallest possible among all possible Orlicz spaces. Now, in particular, if the integral appearing here is convergent, which means that the function a grows fast enough near infinity, then as LA sub n agrees with L infinity. So in fact, here we have embedding to L infinity. And it's easily seen that this condition in the case when A of t is t to the p, so in the classical case, is equivalent to requiring, as expected, that P is strictly larger than dimension. So here we enter the supercritical setting, as I called it before. Moreover, this space that appears here, as I've anticipated, is optimal also for embedding of the classical Sobolev space, where we have the full gradient, and this is the embedding that I've done several years ago for this space. So as I told you, in this framework for when the target space is rearrangement invariant, there is no difference between full gradients and symmetric gradient embeddings. The targets are the same. The optimal targets are the same. So just to see an example, assume that we start with a symmetric gradient space defined in terms of what is called a sigma space, which means that the function A in the definition behaves like a power t to the p times log t to the alpha near infinity. And here, depending on the ranges of p and alpha, we have different kind of targets. So if p is smaller than n, then this space is embedded into the space L p star. This is a Sobolev exponent. And then there is log L again with another exponent here, which depends on alpha and p. If we are in the critical case where p equals n and alpha is subcritical in the sense that it's less than n minus 1, then we have an exponential type embedding with this exponent here. If both p and alpha are critical, which means p is n and alpha is n minus 1, then we have a double exponential space. And finally, if either p is larger than n or p is n but alpha is supercritical, then in fact we have embedding to L infinity. And all the spaces here are optimal in the class of Orlicz spaces. Now, let's go for some further improvement of these results. And before I state it for Orlicz spaces, let me remind you what happens for this classical Sobolev spaces. Now, if P is larger than 1 and less than n, this standard Sobolev embedding with the LP star as a target can be improved. Can still be improved if the target space is allowed to be a more general rearrangement invariant space, which in this case is a Lorentz space, one of the spaces I mentioned before, which here is denoted by LP star P. So Lorentz spaces are defined in terms of two exponents. The first is in a sense corresponding to the exponent in the parallel direct space. The second one provides a final tuning for the spaces. If the two exponents are the same, then we recover the corresponding direct space. If the second exponent is smaller, as in this case, than the first one, then we have a smaller space. So there is monotonicity in the second exponent. And for this special couple of exponents, the Lorentz space is given by this formula, where we have to take the decreasing rearrangement of U, multiply by this negative power of S to the -1 over n, and then we have to take this norm in LP of 0 measure of omega. Yeah. So this is the definition of this space, and please try to keep this in mind, because later for Orlicz spaces there will be a variant of this one that I'll show you. And it turns out that now this embedding cannot be any more improved, at least if the target space is in the family of rearranging invariant spaces. So this Lorentz space is optimal among all rearranging invariant target spaces. Now, I will not mention it here, but there is a similar improvement of this embedding also in the borderline case where P is n. Now, let's go to symmetric spaces. Now, if P is strictly between 1 and n, then because of the identity of this space and the full gradient space, this embedding is still true. But what is interesting is that the corresponding embedding for P equal to 1 is also true, again, even if this space here differs from W11 not. So this embedding holds, which is nothing but this one with P equals to 1. And let me mention that differently from the other ones, this result is a very recent one, just 2 years old. And this is due, it's quite a remarkable result in my opinion, to Daniel Spector and Jean van Schaftingen. Although the same result was announced some years ago in a seminar, but as far as I know, never published by Luc Tartar. And it seems that the approach is similar as the one by Spector and van Schaftingen. And in a sense, the proof is in the spirit of the one by Gallardo-Nirenberg and of some paper by Fournier. And it's based on the restrictions of these functions to lines in Rn, rearrangement, and the clever use of Hilbert type inequalities, basically. But of course, it's not so straightforward. Now, in the same spirit, now we were looking for an improvement of the result I've told you about so far, where the target space was a knowledge space, and trying to find something better, which means optimal rearrangement invariant space for this domain E1LA. This can be described, and again, one needs some formula for the function which has to be used in the definition of this optimal target. Now, to this purpose, let me write the function a in an integral form. So a is a convex function, vanishes at the origin. So this means that this can be written as the integral from 0 to t of an increasing function, small a, which is its derivative. And once a is defined this way, one has to construct another function a hat, which is also given by an integral of a hat small. And a hat is connected to a through its inverse by this formula. So this is even more complicated than the previous one, but again, only the behavior of these functions a and a hat near infinity is important. So all these integrals and inverses can be evaluated asymptotically so far. So a hat can be estimated near infinity. Let me tell you that in general, this function a hat grows less than a, at least may grow less than a, it's never growing faster. And in fact, the two functions are equivalent near infinity and also near 0 if a is far apart in a suitable sense from the critical growth t to the n. And t to the n is critical, as you well know, in the Sobolev type embeddings. So if a is far from Tn in the sense of Matuszewska or Orlicz's indices, but I'm not going to define them, then the two functions are equivalent. Now, with this function a hat, one can construct a Orlicz-Lorentz space analogous to the LP star P I've shown to you before. So this is a norm in that space. And you see the philosophy is completely analogous. We take the rearrangement, we multiply by same power s to the -1 over n, and then we take a norm, which before it was exactly the same as LP. Now, in general, it's not LA, but is this LA hat. And as explained, if A is not critical in a sense, then in fact here we can write LA. But in general, this can be a slightly weaker norm than the original one. And this makes a difference. Now with this notation in place, I can state the result for these spaces. And the result is that one has embedding from E1LA into this Orlicz-Lorentz space and the corresponding Poincare type inequality. And now this target, this Orlicz-Lorentz space here is optimal as it was for W1P and E1P, among all rearrangement invariant spaces. This result for the full gradient Orlicz-Sobolev spaces with the same space here was proved in this paper of mine 7 years ago. So as already mentioned, in this range of targets, having these domains or these domains gives the optimal target space. Now, what about the proof? A key step in this proof for symmetric gradient embeddings is what we call reduction principle. Here is a statement, and the idea is that any embedding of this type can be reduced, is equivalent to a much simpler inequality for one-dimensional functions, so functions of one variable. And
excuse me, and where is the statement?
Sorry?
Where is the statement?
In a moment, it comes.
Ah, okay.
This is just a comment on the statement. And the inequality that will appear, hopefully, is an inequality for an integral operator of Hardy type. Okay, so here's the statement. Given two spaces X and Y, which are rearrangement invariant, these facts are equivalent. So the first one is that we have this embedding from the symmetric gradient E1X into the space Y. The second one is that the same embedding holds if instead of having symmetric gradients, we have full gradients with the same spaces X and Y. And the third statement is this reduction, which says that these two things are equivalent to this inequality here, which is sometimes called the Hardy type inequality because it involves some primitive of one-dimensional function f times this power that has to hold for any non-increasing functions. So it's even restricted to non-increasing functions. In fact, one can show that this inequality for non-increasing function is equivalent to the same inequality for arbitrary non-negative functions, but this is not trivial, this equivalence. Okay, so you see everything is reduced to this for the corresponding one-dimensional spaces, and as you can imagine, this is much simpler than the original problem. Now, given this reduction principle, one can characterize, in a sense, in an abstract way, the optimal target space for among all rearrangement invariant spaces. And this characterization is given by this space that I denote by X1 and goes through this formula. So this is not completely explicit. Why? Because here we have primes in these spaces. Primes stand for associated spaces in the sense of rearrangement invariant spaces. These are, in most cases, the duals of X and X1. Not always. So they not always agree with the topological duals, but in most situations they do. For instance, if X is L1, then X prime is L infinity, and vice versa, which is not the case. So in a sense, X prime is the space that appears in an Elder type inequality for X. This is the simplest way and basically the definition of this space here. So given X, one has to build up the dual, the associate, evaluated this function. U double star is this function which is defined in terms of U star. And then one obtains a norm. And the solution to the problem is again the dual of this, of the associate of this. So this is a way to construct it. Now, given this definition, it turns out that for any space X, this gives you the optimal target for embedding for symmetric gradient spaces. And this is the statement and the corresponding inequality. And this is, in fact, optimal for any X. Now, this is a version for symmetric gradients of a similar result that was proved by David Edmonds, Ron Kerman, and Luboš Pik for the full gradient Sobolev spaces. Now, how to prove the reduction principle? This is another story. Now, let me start with the case of W1x naught. So functions with greater in x that vanishes at the boundary. Now, for these spaces, this reduction principle is rather easy in a sense, because it follows from what is called the Pauli-Asigo inequality, which tells that any norm of this kind of the gradient does not increase if u is replaced by the symmetric rearrangement of u. Symmetric rearrangement means that the new function u star is defined in the ball with the same measure as omega, and is radially decreasing about the origin, and has the same measure. The level sets have the same measure, the corresponding sets of u. So they are equidistributed. So this can be obtained by the...
Andrea, could
Yes.
I ask, where can I find this inequality in such a general situation for arbitrary X rearrangement invariant?
Yes. So it's certainly in some papers of mine with Lubos-Pick and others.
Okay,
I can send you the reference.
Okay, thank you. Mm-hmm.
The classical case, goes back to these papers by Talenti, for instance.
Surely, yeah, I know the classical case. I know.
Good. So it's true for any RI space. Thanks.
Mm-hmm. Okay.
Good. So let's go ahead. So the point is that this kind of inequality fails if you have symmetric gradients. This does not apply. So one has to resort to some other approach or idea. And what was successful is the use of what are called key functionals. Now, these key functionals are important in the rising interpolation theory, and they were also used by Ron Kerman and Lubos-Pick for standard Sobolev spaces when dealing with higher order embeddings. So I'm not going to use it, but just for reference, let me recall that the key function of a couple of norm spaces Z0 and Z1 is defined for functions in the sum of the two and the value of the parameter t larger than 0 as the infimum of the sum of the norm of Z0 and the norm of Z1 in the two spaces, the second one multiplied by t, among all the composition of Z in two functions from the two spaces. Now, this is the definition. Now, the key functional for the couple of the classical Sobolev space W11 and W1 infinity is regarded as a fundamental result in interpolation theory, which goes back to Ron-Devor and Scherer, published in Annals of Mathematics several years ago, and tells us that the key functional for the two spaces at some function u and parameter t is equivalent up to constants to the integral from 0 to t of the rearrangement of u and the rearrangement of the modulus of a gradient. And so quite a simple formula. So a main point in our paper was to find an analogous result for symmetric gradient spaces, which apparently was not known in the theory. And the result for this is the following, that the key functional has exactly the same structure as the one for full gradient spaces, save that, as expected, on the right-hand side, instead of taking the rearrangement of the gradient, one has the rearrangement of the symmetric gradient. And in particular, if one deals with functions in these spaces with a knot in Rn, which means that they are basically with support, with bounded support, or the closure of functions with bounded support, then the term corresponding to u itself can be dropped. So this is in fact equivalent to just this integral of the rearrangement of E of u star.
You mean absolute value of symmetric gradient?
The norm, let's say, because symmetric gradient is a metric, so we're just taking the norm, of course. Mm-hmm. Yes. And also u is a vector, so here is some abuse of notation, as you notice. Thanks for the remark. we have to take norms of these vectors and matrices. Yes.
Mm-hmm.
Now, what about the proof of this key functional? Now here, because of the presence of these symmetric gradients, one has to be careful, and truncation, which can be used for standard Sobolev spaces, doesn't apply here. So we have to resort to what is called Lipschitz truncations for these functions, which is a tool which is used quite a lot in the theory of regularity of PDEs and calculus of variations. And one has this key functional at hand, then the proof is basically as follows. One starts with the endpoint embeddings for these spaces. So the first one is the one that was proved by Spector and van Schaftinger, which tells you that the E11, let's say, is embedded into this Lorentz space. This is one endpoint where the domain space is the largest possible in a sense because we have L1 node. The other endpoint is the opposite one, where the target one is at least locally the best possible because we have L infinity, and the source, the domain for this space is E1 Ln1. This is again a Lorentz space, which is slightly better than Ln, let's say, for which the result is false. Now, starting with these endpoint spaces, one constructs the key functionals for these spaces. So this one is a key functional between Lorentz and L infinity, which is well known in interpolation theory and has this form. This one instead is the new thing, and it's a key functional for this space here, and this space built upon Ln1. So as you remember, our result was with the E1 infinity, but this one can be obtained by the previous one, the one that we proved by some standard or almost standard result in interpolation theory, which is called the Reiteration theorem for key functionals. Anyway, these two expressions can be derived, and then there is a basic key functional inequality, which is the main reason why these key functional are used in interpolation, which tells that if one has an operator, linear or sublinear operator, in our case the identity, which is mapped between a couple of spaces and another couple of spaces, then there is a pointwise inequality for all functions and all parameters of t between the key functionals of the corresponding targets and domain spaces. And this is what we have here. So here we have this pointwise inequality between this expression for the rearrangement and this other expression for the rearrangement of the symmetric gradient. And with some additional computations, one ends up with this reduction theorem. Good.
Excuse me, what is C here?
C is some constant which depends on dimension, basically.
So it is the only dimensional constant.
Yes, yes, it is dimensional.
Okay.
Because here spaces are just L infinity, and so for this one it's just dimensional. Yes. So if I have a few more minutes, let me tell you something about also the other situation where we are dealing with embeddings into spaces of continuous functions. Now, this means, as I've told you before, that I'm dealing with embeddings for these spaces into C sigma, where sigma is some modus of continuity, which is basically an increasing function which vanishes at the origin. Here we may also assume that omega is bounded because we are dealing with local properties like continuity of functions, so this makes things simpler. And the result is the following. So here it's stated for Orlicz spaces. And first, the embedding from this E1 Li space into the space of continuous functions, C0, holds, and we have a corresponding inequality, if and only if this integral of A is convergent. So let me remind you that this condition was exactly the one that we had for embedding into L infinity. So this means that we have embedding into C0 if and only if we have embedding into L infinity. And the condition is still the same, which applies for full gradient spaces. So till now, there is no difference. Situation changes if we look for the modulus of continuity. So now consider a function A that satisfies this condition. We have continuous functions. What about the modulus of continuity? Modulus of continuity is defined as follows. First, we construct these two functions, psi and eta of A, which are defined in terms of the Young conjugate of A. Young conjugate is the one that appears in the Young inequality. So if we take A of t is t to the p, A tilde is t to the p prime, and like Elder inequality. And from this psi and eta, we construct sigma, which is given by this formula. Again, there are integrals, inverses, but now everything is relevant when R is small, because it's a modulus continuity. So only the behavior near zero is important here. And psi and eta at infinity, of course, because it's reciprocal of R. Then we have the embedding of the symmetric gradient to this space defined by sigma A, and we have a corresponding inequality. And the point is that this modulus of continuity is always optimal. Now, the proof of this embedding doesn't follow from the key functional argument. And again, we have a more general statement where instead of Orlicz spaces, we have a general rearrangement invariant space X. And the approach here is by representation formulas. So these formulas in terms of integral operators of risk potential that I hinted before. So the approach here is different. So let me compare
it is difficult.
This result.
It is difficult even to understand why this is an increasing function.
Well, it's not so much big. This psi, you mean?
Yes, not psi, sigma.
Sigma. Yes, but this follows.
No, I trust, but it is not evident.
No, it's true. But if you make some effort and this function psi, for instance, this psi is a convex function. In fact, this is not apparent. But if you make a change of variable, homogenize, make the integral from 1 to infinity, you get it as an integral of a family of convex functions, and it becomes clear that this is a convex and this is also convex. So these are Young functions, in fact, and then using properties of Young functions, one can show that this is increasing. Good. So what about comparison with the embeddings for the standard Orlicz-Sobolev spaces? So the embedding to C0 are the same as I reminded to you. And they hold under this growth condition on A. But concerning the modulus continuity, the situation can be different. And for instance, the problem for the full gradient space, I considered in this paper of mine in '96. And it turns out that the optimal modulus of continuity is given by the formula by the function rho. And this rho is just one of the two pieces, this one that appears in this formula. And it turns out that between the two, sometimes this prevails and other times this prevails. So in general, let me go ahead. In general, this can be a better result because we have just one piece of the function that defines the modulus of continuity.
Am I right that this depends only on the behavior at infinity, and that one also on the behavior of zero?
No, both of them depend also on the behavior near infinity, because here, even if you have integral from 0 to t, then one can modify A near 0. The space doesn't change because omega has finite measure. And again, if you see what happens here, you see r to the n goes to infinity when r goes to 0. So it's the behavior of eta at infinity as well. Now the question, the reason why this may prevail is when we are close to L infinity as a space here. So I'll show you a couple of examples, and with that I'll probably finish, where LA is a very strong norm. And in this case, this term prevails. So here is the situation. So for certain functions A, this space here that we have for the full gradient can be essentially better than the one for symmetric gradients. And as I said, this is the case when LA is close to L infinity. So here there are the examples. So consider the simple situation where we have W1 infinity. So Lipschitz functions. So it's clear that if function is 0, the boundary, so we have embedding from W1 infinity into Lipschitz functions. This is well known. This means that the full gradient is bounded. But if the symmetric gradient is bounded, which means E1 L infinity, then we only have embedding into the space C sigma infinity, where this modulus continuity is not just R. R would be Lipschitz. We have a perturbation which makes this function sigma slightly worse, a logarithmic perturbation near 0. And this is optimal. So there is a gap between these two embeddings. A similar situation is when we start with the full gradient in an exponential space, exponential with power beta. And the target here is similar to this, is still R with a perturbation of logarithmic type, 1 over beta the exponent. But if the symmetric gradient is in exponential beta, then the modulus of continuity is this sigma beta, which is of the same structure, but here you see the power of the log is larger, which makes it grow faster, go to infinity faster when R goes to 0. So this modulus continuity is worse than this one. And these are optimal. So in fact, there is this gap in this kind of target spaces. So I think that my time is basically over. And so I think that this is a good time to stop. There would be some other slides about ideas of proof and other additional results that we use, like extension theorems in bad domains, which are important when functions that are not 0 at the boundary are considered, that we can also deal, and also approximation result, so density of smooth functions up to the boundary in the domains with minimally irregular boundary. But I mean, I'm not going to these details, and I stop here and just thank you for your attention.
Okay. Just at this point, I have a question. All your results, I mean, super critical, the embedding to smooth function, are true for arbitrary domains, or here you need some smoothness of boundary?
Yes, as you expect, and as you notice, you need some regularity of the boundary, which is the case also in the classical Sobolev spaces.
Yeah.
And in fact, we were looking for minimal conditions in some sense. So since you asked me the question, I'll show you. These are what are called the epsilon delta domains. I don't know if you are familiar with this. These are the domains that appear in John's paper about extension of Sobolev spaces. So this means that near the boundary, 2 points can be joined by a curve where the distance in any point of the curve is comparable in a sense to the distance from the boundary.
Is it the same that John domain?
No, it's not John domain. These are called epsilon delta domains.
Mm-hmm.
So John's is not John in this case. And
Yeah,
this,
I understand, but
yeah.
Okay,
and in the literature they are usually called epsilon delta.
Okay, so it is more general domains.
Probably yes. John domains are.
Okay. More questions and comments?
Can I ask questions?
Yeah.
What about antisymmetric gradients? Antisymmetric gradients may be understood as a differential of the corresponding differential form. Yes?
Yes.
Are there some results about antisymmetric?
So about this, I'm not familiar. So typically, these results, so the result that hold for symmetric gradient hold for more general, let's say, operators which satisfy certain algebraic conditions. Now, I don't know if this apply to the antisymmetric part.
I think not.
In fact, this I never seen explicitly stated for this operators. So I'm not sure whether just for the antisymmetric gradient they do apply or not.
Mm-hmm. In this case, of course, you need to factorize up to, no, for instance, to consider only closed differential form or factorize over gradients. Yes.
Yes. Here, I mean, here functions were zero at the boundary. So this apply with other restriction, but otherwise one has to normalize by skew-symmetric matrices. And as you say, in that case, one has a different normalization. Yes, this I didn't check, but that's an interesting question to investigate. Yes.
Yes, because it is natural. Antisymmetric pass just a differential of differential form.
Yes.
With a natural operator.
Okay.
Yes.
Now this we didn't consider, but that's an interesting issue to address.
Okay, thank you.
Okay, more questions or comments? Okay, let's thank the speaker again.
Thank you.
It was very interesting for me, despite the fact that I had problems with my laptop. Well, thank you very much. Так.
Thank you.
Thank you.
Так. Well, now I have. Так, выключайте, ребята, запись.